Now we will see how to find limits of polynomials as x tends to plus or minus infinity. Now there is a very useful principle which states that the end behavior of a polynomial depends upon its highest degree term. For example, suppose I have been given a polynomial as c0 plus c1x plus c to the power cn x to the power n, and I have to find the limit of this polynomial, limit as x tends to minus infinity or as x tends to plus infinity. This principle says that when you have to find this limit will be same as limit x tends to minus infinity or plus infinity cn x to the power n. In other words, what is happening when this polynomial is given, you can effectively forget about these terms c0, c1, c2. Now, why is this principle true? Suppose this is the polynomial c0 plus c1x plus cnx per n. I can take x to the power n outside the bracket, take it common, then what will remain inside the bracket? c0 by x to the power n plus c1 x to the power n minus 1 plus cn. Now as limit x tends to infinity or plus minus infinity, all these terms, x tends to infinity or plus minus infinity, all these terms go to 0. So effectively you will be left with only x to the power n and cn. Effectively this principle says that when you have to find limit of this whole polynomial, you just concentrate on this highest degree term, that is cn x to the power n. Let's see one example based upon this principle. Suppose I have to find limit x tends to infinity 3x plus 5 by 6x minus 8. What I can do, I can divide both numerator and denominator by x. So I will have 3 plus 5 by x and 6 minus 8 by x. Now as x tends to infinity, this 5 by x will go to 0, that is limit x tends to infinity, 1 by x is 0. Similarly this is 0, so I will be left with 3 by 6, that is 1 by 2 is the limit of this rational function. Using the principle discussed in last slide, there is a quick method for finding limits of rational functions as x tends to plus or minus infinity, and this method is that the end behavior of a rational function matches the end behavior of the quotient of the highest degree term in numerator divided by the highest degree term in the denominator. You see, in last slide I had shown that when I have been given this polynomial as x tends to plus or minus infinity, this whole polynomial will be dominated by this term an x to the power n, the highest degree term. Similarly, the polynomial in the denominator will be guided by this term bm x to the power m. So effectively this rational polynomial, if I have to find the limit of this rational function as x tends to plus or minus infinity, I should concentrate only on these two terms an x to the power n and bm x to the power n. So if I have to find limit x tends to infinity fx, then this will be limit x tends to infinity an by bm x to the power n minus m. Now there can be three cases. Case number 1, suppose your n is less than m. So if your n is less than m, then this will go to 0. Why? Because n is less than m, so this will be something like 1 by x to the power m minus n. This m minus n is positive, so 1 by x of this thing as x tends to infinity will be 0. This is case number 1. Case number 2 will be if n is equal to m, then this will be x to the power 0. So any number however large, if it is to the power 0, it will be 1. So the limit will become an by bm. This is second case. And third case will be if your n is greater than m, then this will go to infinity as x tends to infinity. So when I have been given a rational function of the numerator is say of degree n, denominator is of degree m, there are three cases. First case, if this n is less than m, that is numerator is of lesser degree than denominator, limit will be 0. Second case, if the numerator and denominator are of same degree, then this limit will be an by bm, that is the leading coefficient of numerator divided by leading coefficient of the denominator. Third case, if the degree of your numerator is greater than degree of your denominator, limit will be infinity.